Hello, listeners. Welcome to the episode 24 of the Unlocking the Energy Trilemma podcast. Today, Ravi and Jam speak with Conrad Oakey from Florida about the challenges of energy growth. Conrad is the CEO of NovaTech, a provider of data integration and grid automation solutions to electric utilities. Do not miss the full conversation, and please, don't forget to subscribe if you aren't yet. Ravi, Jose, over to you.
Thank you, Ava, and welcome, Conrad, to the Unlocking the Energy Trilemma podcast.
Thanks for having me on. Long-time listener.
So, as we did with all our guest speakers, I would like to ask you about a fact or figure that is related with the Energy Trilemma and the topic we will speak today. What do you bring us?
Well, I think for the big story, and we're primarily a US-based company, but we do have operations in LATAM and Europe and Southeast Asia. But the growth in demand domestically over the next 15 years, whether all the projects in the pipeline actually materialize or not, it seems like it's going to go from a growth rate of 0.2% over the last 20 years to something like 3.5% to 4%. So 20 times increase in how much more generation is going to be added to the grid over the next decade or two. That happening in an environment where, at least on the utility side, about 50% of the experienced engineering talent will be retiring in the next 5 years. So there's this inflection point of, we got to get a lot done, and we have fewer and fewer experienced and qualified engineering people to get it done. Like, that's the environment that we're living and looking at.
That's an interesting observation, Conrad. So in your view, what are some of the biggest forces you see how utilities think about automation, grid control, and operations over the next decade?
I think this load growth is probably the biggest driver, and we can talk a bit about how it's different from previous efforts like the Obama era smart grid initiatives, the IRA initiative. Demand is here, it's real, and it's a pull rather than a technology push. It's a demand pull for solutions, which is creating a willingness to innovate and actually deploy the technologies that have been tested in pilot scale and demonstrated in, academic and sort of small circumstances up until now. But now you actually have demand growth that necessitates looking around for how can we get better utilization of the assets we already have in the power grid is built. I mean, the utilization rate of the grid is built is something around 47%. So building for peak and not doing demand side control in a ubiquitous and consistent way is part of that. But I think, I back up a little bit. I was raised on a farm. And when I wasn't on the farm, I was in the factory, and I'm the second generation CEO of our company. So when I was a kid, if I wasn't on the farm, I would be in the factory, and my dad and his partners were developing the first digital substation power meters. This is 1980. So they were applying digital signal processing to power flow for the first time. And if you go back to, what I would call grid 1.0, the electromechanical grid, it's kind of like we had this old 1950s Ford diesel tractor on the farm, and it was a mechanical beast. And then grid 2.0, I would say, was started in the 80s and 90s, where you started to see digitization. You started to see the ability to monitor and control at a distance. But topologically, you were still in a one-way centralized model. And the grid 3.0, I think, was presented in pilot form and in PowerPoints going back to the Obama era smart grid initiatives, and the IRA effort, I think, was well structured, but it kind of fell on its face in committee in terms of execution. Now you see this demand growth really pulling all those concepts and technologies of ubiquitous digitization and a more multi-directional, multi-stakeholder topology emerging. And in that environment, the situational awareness system, which basically is the SCADA system, that's, what we provide components for utilities, is that if the power grid was a person, the SCADA system would be the nervous system.
Right.
And so that system, you're adding DERMS, distributed energy management systems on top of that. You're adding advanced demand outage management systems, ADMS systems on top of that. You're building all these layers of automated management and response to an increasingly diverse and dynamic distributed power grid. So I think that the forces driving that shift are that demand growth, this proliferation of distributed energy resources down the feeder, coupled with a drive for resilience and the fact that you might lose lines from fires or from storms. There's a sort of a topological shift to, I would call it a macro grid of microgrids conceptually. Like at the far end of grid 3.0 is this, every municipality is sort of semi-autonomous. It can meet its own needs for a certain period of time. And it's connecting to the bulk system as a market participant, less than just a one-way power flow down through wires. So I think that topological shift is finally coming into fruition because you have deep pocket Silicon Valley participants who are demanding time to power the way they would demand compute provisioning from AWS. They're asking utilities to bring additional generation capacity online on similar timescales. And that's just that cultural clash between move fast and break things and keep the lights on is what's playing out in the grid right now in a way that is unique. I don't think these sets of circumstances haven't occurred before. It's something I like.
Conrad, grids are becoming more complex with more renewables and new distributed resources. How do you see the role of automation and control systems to support operators?
We touched on the decrease of experienced staff in the operations and engineering side. So I think, and as you're increasing the number of sources on the grid and their behavior, and they may not be directly controlled by the utility, you may have a lot of behind the meter assets that are doing what they're doing in a uncoordinated or less than coordinated than the utility operators would like way. So I think that there's the gap between the front of the meter world, which is a regulated monopoly, cybersecure environment, and the back of the meter side, where you have everything from data centers to off-grid survivalists with their systems. They're starting to interact, and operators need some way to reliably tap the resources that are not in their utility's direct control. There's an evolving tension between the grid edge. And there are a lot of ideas and people, the Gridwise Architecture Council has a lot of thinking in this direction about, well, should the utility send a request to the grid edge and the grid edge responds, it's a request for more voltage or more capacity and maybe a price, locational marginal price signal. And the grid edge in aggregate responds to that request across a cyber DMZ that doesn't let all the IoT devices and from foreign manufactured and developed software interact directly with the operational systems of the utility. So there's going to be some sort of cyber DMZ marketplace between the utility operators and the grid edge that allow you operators to reliably dispatch and treat behind the meter assets and other DERs as something that they can count on when they need to manage the grid when they have a need.
You raised some very interesting point, and especially around DERs as well. You brought different eras, the Obama era and the IRA and the Biden plan for sustainability and so on. The role of DERs has somewhat shifted. Previously, the objective with a lot of DERs and behind the meter systems was minimizing CO2 footprint. Now it has become almost a off-grid solution that is required to support some of the power needs. It is more of a economic necessity as opposed to a sustainability objective. My first question is, how do you think that has impacted the market at large and market behavior in general? And also, how do you see the balance evolving between a centralized system, control rooms, and more distributed edge-based intelligence that has evolved? What does that mean for grid performance and resilience?
I think you said what was behind the meter for a long time. There was maybe demand response was the limit of what was asked. And We wanted to be able to, in the old days, call up a plant and say, can you turn off for a while or we're going to crash the whole grid. It was a phone call and a okay.
Right.
And at the CNI layer, now you have virtual power plants kind of aggregating air conditioners, HVAC systems, EV batteries that can dispatch back to the grid. All this stuff that was way back in the smart grid, Obama era stuff was visualized. It's now actually starting to turn into executed contracts. I think also that the big change from my perspective, we put solar panels on our farm in 2009. The subsidies were great. Payback on it was 4 years and it was sized to run grid to neutral, right? So, but we weren't being asked, we weren't given a feed-in tariff. We weren't putting twice as many panels in and making money by selling to the utility. We were running grid to neutral. That was what was permitted. I think the technological shift is the continuing decline in the cost of energy storage. As even energy storage made it through the OB3, like big, beautiful bill, let batteries and nuclear kind of continue on their path of development and research and subsidies. And that ubiquity of storage being around changes the renewables can be, the energy market could become a capacity market. You can have power when you need it because the batteries are there. I think that technological deployment of that technology is kind of what has enabled basically new business models to emerge where you can not just look for the occasional peak shaving out of demand response, but you can begin to look to the grid edge and the DERs as reliable sources of power because they're stored. It's stored power, not power when the sun is shining. It's not circumstantial availability. It's dependable.
Do you believe there is room for more long duration energy storage technologies playing a bigger role in the years to come? Or do you believe that the round trip efficiency of battery storage, what you see at the current time, is sufficient to meet all this AI and data center growth?
The generation that data centers are asking for, you drop a 500 megawatt data center into a municipal environment that's used to serving a 20 megawatt total aggregate load of a town, they're going to need every resource that they possibly can get. Now, I'm a fan of hot rocks and energy storage in thermal sense as well. I think advanced geothermal is a dual purpose generation and storage technology. You can just keep the steam contained until you need it. Like there's different ways to move back and forth between electrical power and thermal storage. I don't think that like picking up heavy rocks and having them fall down like grandfather clock style gravity storage is particularly is going to meet the energy density requirements and the response requirements. But there's ways to store energy and take advantage of generation and energy arbitrage, provided that the market that you're operating in has the volatility in prices to reward energy arbitrage, which pretty much only happens in ERCOT and increasingly so in the US. I think that market opportunity is getting eaten up by the arbitrage players that are already there.
Right. Understood.
That's an interesting point. And you have mentioned storage, you have mentioned regulation, arbitrage, capacity markets, but not all the countries have capacity markets or similar tools. And we are trying to run a new grid with old rules. Do you see that there is a gap between policies, regulation, national targets with the reality and the things that we can realistically deploy?
I don't think policy is all that involved with the details of the physics and of a particular feeder. Like they're concerned with outcomes and setting goals and trying to set some broad-based incentives that people figure out how to get from here to there. On the ground and in the substations, and we do a lot of this. 95% of the substations in the US, especially because we're the oldest and most layers of technology waves and stuff in our system, every substation, every feeder is unique, and upgrading it, a component of a specific substation, is a particular system, in a way that minimizes you don't take an outage. Ideally, you don't have to change your engineering drawings. Like when we do an upgrade of an IO panel, we just put printed circuit boards where the wires were landed before and bring the signals up into a modern IO brick. And that allows that system, that component of the system to be modernized, made more cyber secure, have more compute and power in the same footprint without anybody else, any other system really noticing. And I think that stepwise, bumpless transfer of old to modern, that's our bread and butter in the US. I mean, we're always modernizing a substation or a feeder within a substation in a way that it's easy for the engineer to implement, and operationally there's really no hiccup at all. I'll go forward a little bit to say what, on the front end of where that technology for us is heading. We've always been in the business of taking what used to take 3 cabinets of devices and turn it into 1 cabinet of software-based devices. We call it box consolidation. It's just the increase of computational density in the same footprint. That continues to happen. And the latest wave of that for us is virtualization, which is just taking the operating system within our devices and placing it in a virtual container so you can run it in a server with any other virtual device. That technology, that approach to provisioning and utilizing the compute resources that you have is the core enabling technology of data centers. They wouldn't exist as an industry as cost effective as they are. They didn't have that virtualization layer happening to provision compute and reallocate it all the time based on need. That's been, brought into the IT systems of utilities. And we're just starting, we're part of the Virtual Protection and Control Alliance, and they're pushing for the full digital virtual 61850 substation and a server, including protection in substations. Our approach in the US is that DNP is kind of the standard in the US, and you can leverage the benefits of virtualization by adding more virtual applications, analytic applications, throw some AI in there just to say the word AI in this conversation. But that trend overall, it's Moore's law. We've been finding ways to do more compute in smaller spaces with different technologies over time. Virtualization is just the newest, but it is one that we're getting a lot of traction with. It's interesting, when we go to Europe, we don't have to explain what virtualization is. Familiarity with digital substation concepts, and they're, how many devices can you support? How many, data points can you bring in? And in the US, we get questions of how many serial cables does okay, it's a piece of software running in a hardware environment. And so that push toward virtualization that is very well known in the data center world, and data centers probably wouldn't operate without it, making its way into the substation utility side is one of the trends we're trying to have a positive effect on.
Great. And Conrad, I think it has been a fantastic conversation. We would like to close in the same way we do with our speakers. And let me ask you, if you had a magic wand, what would you do to unlock the energy trilemma?
Cheap nuclear fusion.
Okay. Do you believe that SMRs have made sufficient progress in terms of cost, in terms of realization, and eventually supporting the transition?
SMRs, I know that Ontario's putting one in.
Yeah.
VA is going to put one in. There's still a lot of vendors in that space. I think there's still this hangover of, if it was one design and we were standardized on it, and the government was committed to making 100 or 1,000 of them. My favorite thing would be if every military base said, yeah, we're going to put an SMR here, and we're going to buy the first 1,000 and de-risk the supply chain and make, Army bases energy islands of last resort under any circumstance. You would get to that economy of scale of production that SMRs are supposed to be able to get to. They haven't come down in price because we haven't built 1,000 of them yet. And I do think that, I know nuclear has to be part of the clean, resilient future. The demand growth that we need will require nuclear. Probably the closest I've seen to the building 10 AP1000s over the next 10 years, which is what this administration has finally said they want to see. You still have to get utilities to agree to assume that cost and take on a 10 to 15 year development project for a generation source. So yeah, net zero needs nukes. I'm not sure SMRs have achieved what they haven't achieved what they're conceptually supposed to deliver. And I'm not sure how we get from here to there.
Very good. We keep our hope alive. Japan has restarted a number of, mothballed nuclear reactors. So I think your point is well taken there. Yeah.
Yeah, it's got a bit of a branding challenge.
Right.
It takes 10, 15 years to get going. And then if something happens, it takes 10, 15 years again. So I hope it stays steady. And I mean, well, China's putting in 30, right?
Yep.
So it can be done.
Yeah.
Fantastic, Conrad. Thank you very much. We'll follow you and we'll like to listen from you more. Okay.
Right. Like guys.
Thank you very much. Thanks.
We hope you liked this conversation. Follow us on LinkedIn or subscribe for free to the podcast on the platform of your choice, Spotify, Amazon, YouTube, or Apple. Because in the next episode, Ravi and Jam will speak with another expert about the energy trilemma.